Hello everyone and welcome to our channel. In this video I'll be introducing the new topic exponents on our channel under the exponents playlist. So this topic is under numbers, operations and relationships in when referring back to the textbooks. So I'm just going to start off by giving a brief description or background on why we have exponents in the first place. So, mathematicians always look for more efficient ways to write things, meaning they look for ways to allow us to write long sums and long sentences in short and eventually making us save time. So that's why it's efficient. For example, instead of writing 3 plus 3 plus 3 plus 3 plus 3 plus 3 plus 3, and you can even hear it yourself, it just sounds tedious and time consuming, honestly. So instead of writing 3 plus 3 plus 3 so many times, we can write it as 1 2. So we count the number of threes we have, and we have 1 2 3 4 5 6 7. So that's 7 times 3. And that's how you can write 3 plus 3 plus 3 plus 3 plus 3. 7 times 3. So you just count the number of threes and that number times 3. So the number you're adding so many times. Now, what about 3 times 3 times 3 times 3 times 3 times 3? So 6 threes. We times 3 6 times. For this, we can use the exponential notation, which is, I'm going to write in a different color. 3 to the power of 7. No, it's not 7, it's 3 to the power of 6 because our number of threes are 6. In general, so that's how you write 3 times 3 times 3. You just write the number that you're multiplying so many times and to the power of. So in the A, you write how many times you're timesing that number, if it makes sense. So we have a basic representation of a power, meaning a number that's in exponential notation. So I'm going to introduce that right now. So we have A, which is the base. Then we have N, which is the exponent. I'm just going to say exponent. Then we have, so the exponent and the base together make what we call the power. So a power. And so let's refer back to the example I introduced in the previous slide, 3 to the power of 6. So our base would be 3. Our exponent would be 6. So expo. And together we call it a power. So 3 to the power of 6. That's how you'd say it. So 3 to the power of 6. So what does a to the power of n mean? It means we multiply a n number of times. So we multiply a n number of times. Meaning, let's take 4 to the power of maybe 6. We'd say 4, that's a, right? Because this is our a and that's our n. So that's 4 times 4 times 4. How many times? 6 times. That's our number of n. So times 4 times 4 and times 4. So that's what a to the power of n means, or exponential notation means. And can you see that it really does make things better and it's more efficient because we don't waste time writing. So this number can actually be 4 to the power of 60, and that can take you a very long time to write all those 4s down. So it makes life easier for us. Now let's have a look at exponential rules. So the laws of exponents. Our first one is x to the power of 0. Any number to the power of 0 is 1. Meaning 1 to the power of 0 is 1. 10 to the power of 0 is 1. 6 to the power of 0 is 1. 999 to the power of 0 is 1. 1 million to the power of 0 is 1. Anything to the power of 0 is 1. Let's have a look at our second law of exponents. Anything to the power of 1 is that number. And yes, our second law is anything to the power of 1 is that number. So x to the power of 1 is x. 9 to the power of 1 is 9. 5 to the power of 1 is 5. 1 million to the power of 1 is 1 million. 99 to the power of 1 is 99, is that number. So anything to the power of 1 is that number. Then we have a look at the law 3. So law 3 is a to the power of m times a to the power of n is equals to a to the power of m plus n. So when multiplying two powers of the same base, that's why we have a, then we leave the base the same and add the two exponents. For example, let's take 2 to the power of 3 times 2 to the power of 4. Meaning it's the same base which is 2 and 2. So in this case a and a, but our m and n are different. So 3 and 4 is different. So then our answer is going to be 2, which is the a, to the power of m, which is 3, plus n, which is 4, and that's equals to 2 to the power of 7. And you can double check that by doing that. So 2 times 2 times 2, 3 times 2 times 2 times 2 times 2, 4 times. If you add the 2's, 1, 2, 3, 4, 5, 6, 7, you get that we are saying 2 times 2 times 2 times 2, 7 times. So using the rule, we get 2 to the power of 7. Can you see why the rule works? Now let's have a look at maybe 2 examples and then we move on to our fourth law. So we are going to have 2 to the power of 3 and the base can be anything. In this case I'm choosing 2, and for the next example we can use another number. So 2 to the power of 3 is 2. You don't even have to expand it, so we go, because the law says when the two bases are the same, then you are welcome to say the base to the power of one exponent plus the other exponent, which is 2 to the power of 8. Let's have a look at our second example, which is 3 to the power of 4 times 3 to the power of nothing. So if you simplify that, that's the same base. What are the exponents? In this case we have exponent 4, and in this case we have exponent 1. So whenever a number does not have an exponent, the exponent is automatically 1, because if you say 3 to the power of 1, based on the second rule that I just introduced in the previous slide, we see that 3 to the power of 1 is still 3, so we didn't change the value, but it has a power of 1. So we have 3 because that's the base to the power of 4 plus 1, which is 3 to the power of 5. And that's just how you use law 1. This rule can be extended to more than 2 powers multiplied together, meaning we can have 2 to the power of 5 times 2 to the power of 3 times 2 to the power of 2 times 2 to the power of 1, and you will have 2 to the power of 5 plus 3 plus 2 plus 1, and altogether you will get 2 to the power of 5 plus 3, 8 plus 2, 10, so 2 to the power of 11. And so it does not have to be 2, like 2 times 5 times 2 times 3. You can have 2 times 5 times 2 times 3 times 2 times 2 times. You put all those 2's together to simplify it. That's why this exponential notation is efficient and makes life easier. Now we have a look at our fourth law. So our fourth law has to do with dividing powers of the same base. So this is how our rule is written. So a to the power of m divided by a to the power of m. What do we do when we have the same basis? We say a to the power of m minus m. And so let's look at 3 to 4 examples on how you would solve problems if the case was that. So we get 2 to the power of 8 divided by 2 to the power of 3 would be 2 to the power of 8 minus 3. And the answer would be 2 to the power of 5. And 2 to the power of 5, if they asked you to simplify further, then the answer would be 32. Now let's have a look at another example. Let's have a look at x to the power of 8. So we can have unknowns and we can have knowns. So we can have the base can be an unknown or not an unknown. Same with the exponent. It can be, they can give us the exponent or they can give it up to us as an unknown. So we should be able to use the rule even when it is like that. So x to the power of 8 divided by x to the power of 2 would be x to the power of 8 minus 2 is 6. So x to the power of 6, because we said x to the power of 8 minus 2 is x to the power of 6. And that would be our answer. Then we get when the exponent in the denominator is greater than the exponent in the numerator. So when the exponent, so in this case all our exponents were bigger than the, so can you see that? I'm gonna circle it with yellow. So you can see that the exponent, this is the numerator, and the numerator has an exponent that is 8 and the denominator has an exponent of 2, meaning the numerator's exponent is bigger than meaning the value of the numerator is bigger than the value of the denominator. In this case, our 8 and 3, 8 is bigger than 3. Now what happens when the smaller one is on top and the big one is on the bottom? Then you'd write it as, so the rule still applies, but now you'll have 1 over a to the power of the 8 minus 2. So this 2 goes down and you have 8 minus 2. When this exponent is smaller than the one on the bottom, then that's what you do. And your answer would be 1 over a to the power of 6. So it all depends on if the exponent is bigger. So you take the bigger one and you subtract it from the smaller one. You take the big one and subtract the smaller one from it. Yes. Now, I just want to prove or just elaborate why we say when it's bigger. So let's say we have, so now let's put value so that I can prove it to you, or we can keep it as a or x. So let's say x is equals to, let's say 3 over x is equals to 8. If we expand this, we get x times x, and if you don't know, that dot represents a multiplication. So x times x divided by how many x's on the bottom? 8x. So 8x times x times x times x times x times x times x times x. So we have that, right? 2, 4, 6, 8. Right? So what does that mean? It means we can, let's take a different color so we can see what we're doing. We can cancel that, cancel that, cancel that x, cancel, because there's multiplication over multiplication, meaning it's one term over one term, right? So we cancel that x, cancel that one, cancel that one, cancel that one, cancel this one, and cancel that one, and we get that our answer is here. There's only one now, so it's 1, right? So if you cancel everything, you don't stay with 0, you stay with 1. And on the bottom we have 1, 2, 3, 4, 5. So that's x to the power of 5. Because we have learned that if it's times, 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 you can say 1 plus 1 plus 1 plus 1 plus 1, and that's 5, x to the power of 5. And that's why we say when the exponent on top is smaller than the exponent on the bottom, then you say 1 over the answer. So the easier way to learn this is just look at which one is bigger. So in this case it was x to the power of 8, and so which one should come down? The smaller one. So 8 minus 3. In this case, which one should go up or down? In this case 2 must go down because 2 is smaller. In this case 2 must go up because 2 is smaller. So the smaller exponent goes to the bigger exponent, and then we subtract it from each other. Now let's have a look at our low 5. Yep, low 5. Low 5 states that if it's a to the power of m, and that whole power has an exponent of n, then you are allowed to say a is equals to m times n. So a is equals to m times n. Now let's have a look at examples. So we have 2 to the power of 3 to the power of 4. If we expand this, this is 2 to the power of 3 times 2 to the power of 3 times 2 to the power of 3 times 2 to the power of 3. And if you simplify it further, we learn that you add, if it's the same base, so I'm going to use a different color, same base, you can add the exponents. So we're going to say 3 plus 3 plus 3 plus 3, which we know is 12. So it's 12. So let's quickly write that, and it's going to be 2 to the power of 12, right? So let's confirm if it's the same thing with this. So let's use the rule that we just got. So we say 3 to the power of 4, right? And if we use the rule that we got in green, circled in green, we multiply the two exponents. So it's going to be 2 to the power of 3 times 4, which is 12. So it makes sense. Can you see why the rule works or makes sense? Let's have a look at a few more examples, maybe 3 examples to better understand this concept. And remember, they can give you exponents, they can give you unknowns, and the unknowns can be in the exponent or in the base. They can also give you the values, so you must be able to work with both. So I'm going to do examples that need us to do that. So our first one is 2 to the power of 3 in brackets and to the power of 5. And if you simplify it, that's 3 times 5, so it's 3 times 5, which is 2 to the power of 15. Let's have a look at the second example, which is x squared to the power of 4. And if you simplify it, that's x to the power of 2 times 4, which is 8, so x to the power of 8. Let's prove why it's like that. So that's x squared times x squared times x squared times x squared. And we said we can add if the bases are the same. So x to the power of 2 plus 2 plus 2 plus 2. 2 plus 2 is 4. 4 plus 2 is 6. 6 plus 2 is 8. So it proves it right. Now let's have a look at our last example before we go to our low 6. So we have, this one is a bit complex, but same thing. So x squared to the power of 4, all of that to the power of 3. Now, these exponents are proven, they prove it to be easier, to make it easier to do such things. Can you see how tedious and time consuming this would have been if we kept expanding this and trying to figure out the answer? That's why we have such a rule that says if we have a to the power of m and all that's to the power of n, then you're allowed to say a to the power of m times n. So let's have a look. We have to, looking at this example here, we have to break it down into two because it's a lot of exponents. So we are going to look at the inner part first, then we're going to look at the outside. So we're going to look at the red part first, which is x squared to the power of 4, right? And that answer is x to the power of 2 times 4, which is x to the power of 8, right? So that is x to the power of 8, right? So we're going to replace x to the power of 8 with this. So we're going to replace this whole bracket here in red with x to the power of 8. So we're going to have x to the power of 8 to the power of 3. And we use that same rule, and it's going to be 8 times 3 is 24. So x to the power of 24, sorry about that. So it's going to be x to the power of 24. Now let's have a look at law number 6. In law number 6, we raise a product to a power, meaning we raise, so this is a product a times b, so the numbers can be different, that's why we indicate it as a times b. So a product, we raise that product to a power n, meaning we can say a to the power of n times b to the power of n. So we can write it as that. We can expand it by doing the following. So let's have a look at and then solve it from there. So let's have a look at some examples that use the law a times b to the power, all to the power of n, which is equals to a to the power of n times b to the power of n. So we're going to look at 2 times 3 to the power of 4, which is equals to 2 to the power of 4 times 3 to the power of 4. And that's just how you do it. Now let's have a look at more examples to better understand the concept of law number 6. So it's going to be ab to the power of 5, which is equals to, and if you recall, or if you know, if you didn't know, between the a and b there's a multiplication. So it's still the same thing. So a to the power of 5 times b to the power of 5. That's how you expand it. You don't even have to put that dot inside. And then let's look at our next example, which is 2x to the power of 3. 2 times x, that means there's a times there. So the 2 is raised to the power of 3 and the x is raised to the power of 3 too. So it's 2 to the power of 3, x to the power of 3. And if you expand it, that's 8, because 2 to the power of 3 is 8, x to the power of 3. That's the answer. Let's have a look at a more complex question that requires to use law number 6. So that's going to be, let's use red, negative 3abc to the power of 2. So we're going to separate them. So negative 3 squared times a squared times b squared. So you multiply everything together, and each item or term is to the power of 2, or it's 2 squared. Then we simplify. So negative 3 squared is 9. So negative 3 times negative 3 is a positive 9, because negative times a negative is a positive. And then a is going to stay a squared, b squared, c squared. And so that's our answer for this question. Now let's have a look at law number 7. Law number 7 states that if you have a base and it's to the power of a negative number, so negative n, then you can say 1 over a to the power of n, positive n. So we are trying to make the negative positive so that we can simplify. So we're trying to make this negative here to be a positive exponent so that we can simplify it. So let's have a look. So we are using this rule. A to the power of negative n is equals to 1 over a to the power of n, positive n. So now let's have a look at an example. So 2 to the power of negative 2. We don't know 2 to the power of negative 2, but our calculator knows 2 to the power of negative 2. We don't know things like 2 to the power of negative 6. That's why we are trying to make it simple. So we make it simple by putting it over 1 so that the exponent can become a positive and we can expand it. So it's going to be 2 to the power of positive 2. And only after that, sorry, that's not an 8, that's a 2. So the power of 2, and only after that we can say 1 over 4. But if you were to look at 2 to the power of negative 2, most of us would not get the answer by not using this exponent rule. That's why it is there. So let's have a look at another one. So 3 to the power of negative 2. You'd say 1 over 3 to the power of positive 2, and then that's 1 over 9, because 3 times 3 is 9. Let's have a look at our last example. So it's going to be 3 to the power, let's say 3 to the power of 5 is equals to negative 5 is equals to 1 over 3 to the power of negative 5. Positive 5, because it's now over 1. And that's 1 over 3 to the power of 5. So that is it for this video. Thank you all for watching. See you in our next video as we tackle examples and introduce more concepts when it comes to exponents and better understand the whole exponent or exponential notation concept. See you in our next video. Bye.